Okay, in today's notes we're going to compare linear and exponential functions. So at the top of the page it says linear functions are based on repeatedly adding the same amount. Okay, so recall the standard form of a linear equation is y equals mx plus b, where m is your slope, and b is the y-intercept. The whole idea of repeatedly adding the same amount means your rate of change, or slope, is constant. Okay? Exponential functions are based on repeatedly multiplying by the same amount. So your rate of change is not constant. Okay? It's going to be increasing or decreasing by the same factor. Okay? Or multiplying. The standard form for your exponential is y equals a times b to the x. Remember, the x is in the exponent, where your a value is the starting amount or initial value, and the b value is your rate at which you grow or decay. Okay, your rate of growth or decay. So we have two examples. It says the tables below represent a linear and an exponential function. After you determine which type of function the tables represent, write their equation in standard form. So if we look at table number 1, okay, the x's are increasing consecutively, okay, 0, 1, 2, 3, 4. They differ by 1. And in table 2, the x values also increase by 1, and they are in consecutive order of 0, 1, 2, 3, and 4. What's different is that your y values here, going from 5 to 10, 10 to 20, 20 to 40, that change of y is not the same. So here, we're multiplying by 2 each time from one value to the next. So I'm going to, instead of writing the dot 2, I'm just going to make note that we're multiplying our y values by 2. Here, our y values from one to the next are increasing by 3. So we're adding 3 to our y values. So if I just take a look at these 2 points, okay, if we want to look at rate of change, so change of y over change of x, this increased by 5, from 5 to 10, over a change of 1, so I have a rate of change or a slope of 5. But then looking at the last 2 points, okay, change of y over change of x, we have an increase of 40 to 1. So your rate of change, okay, is not constant. And since we're multiplying by 2, this is an exponential function. With the table 2, if I look at the first 2 points again, that rate of change, change of y over change of x, well, y, we're increasing by 3, so we have a difference of 3 over a difference of 1, which is 3. At the end, looking here at these 2 points, our rate of change 17 to 20, we're still increasing by 3 as we increase by 1. We have the same slope all the way through. So therefore, this is going to be a linear function. Now to write the equations. Let's start with the linear, as that's the one we just finished. So y equals mx plus b. We just calculated a slope. So we know our slope is 3. And then our b value, so right here is the point 0, 8. And the y-intercept always has an x value of y, as that's the point where the graph crosses the y-axis. So our b value is 8. So putting it together, y equals mx plus b would be y equals 3x plus 8. So over here, looking at our starting value or y-intercept, we have an a value of 5. And our b, our rate, okay, or our, this time, repeatedly multiplying, okay, or the factor that we, so the factor we increase by is 2. We keep doubling the y value. So our b value is going to be 2. Okay, that's the factor of which we increase or decrease. So putting this together, y equals, so we have a starting value of 5, and each y value is doubled, so it's times 2 to the x. Number 2, it says the two tables below represent a linear and an exponential function. Compare their rate of change over the intervals, and then what do we notice in part B? Okay, so let's look at table 1 versus table 2. We look at the x's, they're still increasing by 1. So in looking at the y values, here, to go from one to the next, that's a continuous increase by 4. So we're adding 4 from one to the next. Over here, well, 8 is half of 16, 4 is half of 8, 4 times 1/2 is 2, 2 times 1/2 is 1. So here we're multiplying by 1/2. Okay, so the one on the left is linear, and the one on the right, or table 2, is exponential. So compare their rate of change over the interval from -2 to 0. So for table 1, and table 2 for each, the points we're looking at in table 1, remember from -2 to 0, so we're taking the 2 points that have an x value of -2 and 0. So in table 1, when x is -2, y is -4. When x is 0, y is 4. So change of y over change of x, okay, your rate of change equals 4 minus -4. I subtracted the top from the bottom, over 0 minus 2. 4 minus the -4 turns into a positive 8, 0 minus 2. Okay, I forgot to have 0 minus the -2. That also becomes positive, and 8 over 2 is 4. In table 2, when x is -2, your y is 16. And when x is 0, your y is 4. So our rate of change here, I'm going to subtract in the same order. So 4 minus 16 over 0 minus -2. 4 minus 16 is a -12. 0 minus a -2 is a positive 2. Divide, and we get -6. Compare their average rate of change. Well, table 2, okay, has a greater rate of change. I'm realizing it's negative, but negative is just indicating the direction, okay, versus negative versus a positive. So table 2 has a greater rate of change. And we can also note that the rate of change for table 1 is positive, and the rate of change for table 2 is negative. Okay, so there are two things about those two rates of change. All right, part B. We have a different interval, so I'm going to use orange since I was highlighting in a table. Our intervals from -2 to 2, so we're looking for those points that have an x value of -2 and 2 on both of those tables. We want to find the y value that goes with each of those points. So in table 1, when x is 2, once again we have a y value of 4. But this time, when x is a positive 2, we have a y value of 12. On table 2, we're looking at the same x value of -2, which has a y value of 16. And then when x is a positive 2, we have a y value of 1. So calculating the rate of change, we have, so rate of change, rate of change, rate of change, rate of change equals. All right, let's write the fractions for each and simplify them all at the end. So, whoa, I actually don't need 4 rates of change. I only need 2. Oops, let's get rid of that. All right. Oops, I can actually get rid of those 2 semicolons. I got a little carried away with the rate of change because we're looking at the rate of change for these 2 points. So y2 minus y1 would be 12 minus 4 over 2 minus -2. So we end up with oops, I caught one more mistake. Up here, the y value is a -4. Okay, so we're subtracting a negative. 12 minus a -4 turns out to be 16. And then 2 minus a -2 is 4, and 16 over 4 is 4. So we have a positive rate of change, so indicating a positive slope. And then here, 1 minus 16 over 2 minus -2. So we end up with -15 over 4, which gives us a value of -3.75. Or you could leave it as 15/4. Okay, so that's a negative slope. So here, our rate of change in table 1 is greater. So table 1 has a greater rate of change. And then table 2 has a negative rate of change. Okay, and table 1 has a positive rate of change. Okay, so table 1 with the linear, let's go back to table 1, and I'll highlight in yellow. So for this linear equation, it's going to have a positive slope all the way through and actually be a line. Table 2, with it being exponential, yes, it goes down a little bit, but the curve is actually going to look like this. So we may have just a little fraction of that exponential curve. And then table 1, okay, table 1 is linear, so yes, we will see the line. And then table 2. We also have the negative slope. So in our curve looking like that. On the back side, it says examine each of the following situations and determine if the situation is a linear type of situation or exponential. So let's get rid of this here. And then the first one, 2x plus y equals 12. Well, in subtracting the 2x, we end up with y equals 12 minus 2x, or negative 2x plus 12. Because we have an x and a y, and they're not in the exponent, and we can solve for y and have it in terms of mx plus b, this is linear. Number 2, there are currently 12 rabbits on a farm, and this population will increase by 24% each year. So if it's increasing by a rate of 24% each year, that's going to be exponential growth. Whoops. Number 1, or no, part C, y equals 1 to the x. Well, this is kind of tricky. I realize the x is in the exponent, but even if you do 1 to the first power, 1 to the second power, 1 to the third power, and so on, you're going to end up with y equals 1. So that was tricky because it had a 1 as its base. That's going to be linear. Looking at the table, so x's are increasing by 1. Looking at the y values to go from 1 to 1/3 to 3, 3 to 9, 9 to 27. We are multiplying by 3. And as your x values increase, so let's make note, as x increases, y is also increases. Okay, so that's going to be exponential growth. Y equals 3.5 times x. Well, since our b value is greater than 1, that's also going to be exponential growth as we see the x in the exponent. And b is not a 1. That's the only time it's tricky. F. The population in Genoa City increases each year by 120 people. So if you think of your x and y, okay, so we're at 0, 1, 20, and then at year 1, we're going to increase by, so 240. Year 2 plus 120 is 360, so on and so forth. Since, again, you're adding the same amount, this is linear. Your rate of change is constant. G. A height of a softball is modeled by the equation h equals negative 16t squared plus 24t plus 1, where h is the height in feet and t is the time in second. Well, this is a quadratic function as we just finished the unit, so this would be other. And let's make note that this is a quadratic, as it was degree 2. H. The length of a rectangle is 5 times its width. Okay, so we have a rectangle, the length is x, the length is 5 times x. So if we look at this in terms of a table, okay, so x and y, so if we say x is the width, right? So if x is, say, 2, then it says the length is 5 times the width, so that would be 10. If the width was 3, 5 times 3, the length would be 15. If the width is 4, the length 5 times 4, 20. If the width 5, 5 times 5, 25. So as our widths increase by 1, we notice to go from 1y to the next, we're adding 5, which would be linear. So it helps sometimes to make up a table to see what's actually happening. And that one, we knew the length of a rectangle is 5 times its width, so the relationship between the two, okay, is a linear relationship. In I, 300 plus 0.6 to the x. Now because of the x, it's exponential, and our b value is 0.6. And because that value is less than 1, we're going to see exponential decay. And the last one, of course, is other, and from the last unit, that's a quadratic.